Hey everyone, if we recall from the first introductory video, we talked about how differentiation is basically like, calculating the gradient where we have a point on the graph and then we take this point that gets closer and closer to this point, resulting in the gradient, the line of the gradient, to be almost as close to the tangent of the line at this point, let's say this point x. And then we came up with a formula, which is basically just the gradient between the 2 points, fx plus h minus fx over h, such that the h approaches 0, and then we have the 2 points being very close to each other, therefore giving us the gradient, and hence dy dx. And this is what we call by the first principle of differentiation, and it's only found in the H2 math syllabus and not in the H1 nor in the A math syllabus. So for those of you O-level students or H1 math students, you can choose to not watch this video, but I guess if you want to watch it, good for you then. You'll learn a lot more here. So we have dy dx equals the lim as h approaches 0, fx plus h minus fx over h. And of course, as we mentioned just now, rate of change of y over rate of change of x. And let's just put this in practice, shall we? We know that we have a function y equals x squared. The derivative is 2x. Now, there'll be questions that ask you to prove this, find a derivative using first principle. So we just, do the same thing. So we have lim h approaches 0, x plus h squared minus x squared over h. Expanding x plus h squared gives us x squared plus 2h, x plus h squared minus x squared, and therefore we will get back, obviously putting in the lim again, 2hx plus h squared over h. We factorize out h from the top, and then you get lim h approaches 0 because I can factorize out h, so I get back 2x plus h. Now then, we apply the limit to h. As h approaches 0, this would then become 2x. And you notice it's exactly the gradient here. Reason why we don't apply the limit too early is because we all know that you cannot divide by 0, and therefore we have to get rid of the h in the denominator first before we can apply the limit. And this is actually one example of your first principles, differentiation by first principles. I'll show you another example, which is actually the power rule, the simple power rule where we have x power of n. We know that the derivative is dy dx equals to nx power n minus 1. How do you prove it using first principles? Same thing, dy dx, lim h approaches 0, fx plus h minus fx, so I'll get x plus, this is a plus sign, h power of n minus x power of n over h. This is a binomial expansion, and therefore we have x power of n minus x power of n, so I'll cancel this out. So I start from the second term onwards, I'll get n choose 1, x power of n minus 1h plus n choose 2, x to the power of n minus 2h squared, plus so on, plus n choose n minus 1, which is actually just n, x h n minus 1, then lastly h to the power of n. And this whole thing over h, of course we haven't applied the limit yet, so limit of h approaches 0. Notice that for this set of terms, there are at least one h in each term, so we therefore can factorize out at least one h. I mean there's only one h you can factorize out, so again, limit h approaches 0, we then get n x n minus 1 plus n choose 2, x n minus 2h plus all the way to plus n choose n minus 1, which is basically just n again, x n minus 2 plus h n minus 1. X and then h n minus 2 for this term. Then we apply the limit because we've gotten rid of the denominator, and you realize from these terms, we have h for each of the terms. So these terms will all become 0, 0, 0, 0, 0, 0. And at the end, we get n times x to the power of n minus 1. And this proves the power rule through first principles, and hope that through these two examples, we have better understanding of first principles. Of course, we can swap H with another letter, like for example G or K, and you can put that. But when you learn a higher math, if you're ever interested, or if you're sadistic, then you realize that for calculus, we like to use the letter H to represent height, especially when it comes to some of your integration. So yeah, this is the differentiation by first principles.